Troubleshooting is a form of problem-solving, often applied to repair failed products or processes. It is a logical, systematic search for the source of a problem in order to solve it, and make the product or process operational again. Troubleshooting is needed to identify the symptoms. Determining the most likely cause is a process of elimination, eliminating potential causes of a problem. Finally, troubleshooting requires confirmation that the solution restores the product or process to its working state. In general, troubleshooting is the identification of diagnosis of trouble in the management flow of a corporation or a system caused by a failure of some kind. The problem is initially described as symptoms of malfunction, and troubleshooting is the process of determining and remedying the causes of these symptoms. A system can be described in terms of its expected, desired or intended behavior. Events or inputs to the system are expected to generate specific results or outputs. Any unexpected or undesirable behavior is a symptom. Troubleshooting is the process of isolating the specific cause or causes of the symptom. Frequently, the symptom is a failure of the product or process to produce any results. Corrective action can then be taken to prevent further failures of a similar kind. The methods of forensic engineering are especially useful in tracing problems in products or processes, and a wide range of analytical techniques are available to determine the cause or causes of specific failures. Corrective action can then be taken to prevent further failure of a similar kind. Preventative action is possible using failure mode and effects and fault tree analysis before full-scale production, and these methods can also be used for failure analysis aspects. Usually troubleshooting is applied to something that has suddenly stopped working, since its previously working state forms the expectations about its continued behavior. So the initial focus is often on recent changes to the system or to the environment in which it exists. However, there is a well-known principle that correlation does not imply causality. Therefore, troubleshooting demands critical thinking rather than magical thinking. It is useful to consider the common experiences we have with light bulbs. Light bulbs burn out, more or less at random. Eventually, the repeated heating and cooling of its filament, and fluctuations in the power supplied to it, cause the filament to crack or vaporize. The same principle applies to most other electronic devices, and similar principles apply to mechanical devices. Some failures are part of the normal wear and tear of components in a system. A basic principle in troubleshooting is to start from the simplest and most probable possible problems first. This is illustrated by the old saying, "When you see hoof prints, look for horses, not zebras," or to use another maxim, use the KISS principle. This principle results in the common complaint about help desks or manuals, that they sometimes first ask, "Is it plugged in and does that receptacle have power?" But this should not be taken as an affront. Rather, it should serve as a reminder or conditioning to always check the simple things first before calling for help. A troubleshooter could check each component in a system one by one, substituting known good components for each potentially suspect one. However, this process of serial substitution can be considered degenerate when components are substituted without regard to a hypothesis concerning how their failure could result in the symptoms being diagnosed. Simple and intermediate systems are characterized by lists or trees of dependencies among their components or subsystems. More complex systems contain cyclical dependencies or interactions. Such systems are less amenable to bisection troubleshooting techniques. It also helps to start from a known good state, the best example being a computer reboot. A cognitive walkthrough is also a good thing to try. Comprehensive documentation produced by proficient technical writers is very helpful, especially if it provides a theory of operation for the subject device or system. A common cause of problems is bad design, for example bad human factors design, where a device could be inserted backward or upside down due to the lack of an appropriate forcing function, or a lack of error-tolerant design. This is especially bad if accompanied by habituation, where the user just doesn't notice the incorrect usage. For instance, if two parts have different functions but share a common case so that it is not apparent on a casual inspection which part is being used. Developing troubleshooting procedures in advance allows sufficient thought about the steps to take in troubleshooting and organizing the troubleshooting into the most efficient troubleshooting process. Troubleshooting tables can be computerized to make them more efficient for users. Some computerized troubleshooting services immediately show the top 10 solutions with the highest probability of fixing the underlying problem. The technician can either answer additional questions to advance through the troubleshooting procedure, each step narrowing the list of solutions, or immediately implement the solution he feels will fix the problem. These services give a rebate if the technician takes an additional step after the problem is solved. Report back the solution that actually fixed the problem. The computer uses these reports to update its estimates of which solutions have the highest probability of fixing that particular set of symptoms. Half-splitting. Efficient methodical troubleshooting starts with a clear understanding of the expected behavior of the system and the symptoms being observed. From there, the troubleshooter forms hypotheses on potential causes, and devises tests to eliminate these prospective causes. This approach is often called divide and conquer. Two common strategies used by troubleshooters are to check for frequently encountered or easily tested conditions first. This is often referred to as milking the front panel, then bisect the system. This latter technique can be particularly efficient in systems with long chains of serialized dependencies or interactions among its components. It is simply the application of a binary search across the range of dependencies and is often referred to as half-splitting. Reproducing symptoms. One of the core principles of troubleshooting is that reproducible problems can be reliably isolated and resolved. Often, considerable effort and emphasis in troubleshooting is placed on reproducibility, on finding a procedure to reliably induce the symptom to occur. Intermittent symptoms. Some of the most difficult troubleshooting issues relate to symptoms which occur intermittently. In electronics, this often is the result of components that are thermally sensitive. Compressed air can be used to cool specific spots on a circuit board, and a heat gun can be used to raise the temperatures. Thus, troubleshooting of electronic systems frequently entails applying these tools in order to reproduce a problem. In computer programming, race conditions often lead to intermittent symptoms which are extremely difficult to reproduce. Various techniques can be used to force the particular function or module to be called more rapidly than it would be in normal operation, while other techniques can be used to introduce greater delays in, or force synchronization among, other modules or interacting processes. Intermittent issues can be thus defined. An intermittent is a problem for which there is no known procedure to consistently reproduce its symptom. Stephen Litt. In particular, he asserts that there is a distinction between frequency of occurrence and a known procedure to consistently reproduce an issue. For example, knowing that an intermittent problem occurs within an hour of a particular stimulus or event, but that sometimes it happens in 5 minutes and other times it takes almost an hour, does not constitute a known procedure, even if the stimulus does increase the frequency of observable exhibitions of the symptom. Nevertheless, sometimes troubleshooters must resort to statistical methods, and can only find procedures to increase the symptom's occurrence to a point at which serial substitution or some other technique is feasible. In such cases, even when the symptom seems to disappear for significantly longer periods, there is a low confidence that the root cause has been found and that the problem is truly solved. Also, tests may be run to stress certain components to determine if those components have failed. Multiple problems. Isolating single component failures which cause reproducible symptoms is relatively straightforward. However, many problems only occur as a result of multiple failures or errors. This is particularly true of fault-tolerant systems, or those with built-in redundancy. Features which add redundancy, fault detection and failover to a system may also be subject to failure, and enough different component failures in any system will take it down. Even in simple systems, the troubleshooter must always consider the possibility that there is more than one fault. Note that while we talk about replacing components, the resolution of many problems involves adjustments or tuning rather than replacement. For example, intermittent breaks in conductors, or dirty or loose contacts, might simply need to be cleaned or tightened.